You have probably seen the animation. A spaceship stretches into a thin ribbon of spaghetti and disappears into the dark. We call it spaghettification. But that is the myth. The truth is far stranger. That violent stretch is not what kills you first, and under the right conditions, it may never happen at all. What actually happens to you doesn't depend on speed or luck. It all comes down to size, the mass of the beast. In 1783, in Yorkshire, an English rector named John Michell sat by candlelight and worked out the mass of an object so dense that not even light could escape it. Einstein wouldn't formalize the physics for another 130 years. Michell called it a dark star. Today, we call it a black hole. When you drift towards one, three things decide your fate: how massive it is, how close you get, and how much time you have left. A stellar mass black hole is a dying star's corpse, several suns crushed into a ball just a few kilometers across. Because the sphere is so tiny, gravity doesn't pull evenly. Your feet, just a few feet closer to the core, feel millions of times more pull than your head. The tidal forces pull you into a thread thinner than spaghetti, tearing you apart in a fraction of a second, faster than pain can even register. Now look at Sagittarius A star, the supermassive monster at the center of our galaxy, holding the mass of 4 million suns. Because its event horizon is millions of kilometers wide, the gravity across your body is nearly uniform. Here, crossing the edge would feel like floating through empty air. We proved it was there by spending 16 years watching a single star, S2, whip through the darkness around an invisible anchor. That patience won the Nobel Prize in 2020. 2 years later, the Event Horizon Telescope delivered proof at last, the first direct image of the shadow itself. The boundary they mapped, the event horizon, is not a solid wall. It is simply a number, the mathematical point where escape velocity exceeds light. This is the point where signals die. No radio wave, no flash of light, no trace of information can ever travel back out. Yet you wouldn't feel a thud or see a barrier. You would keep falling, keep breathing, and keep watching your instruments hum. From this moment on, your reality and the outside universe split into two clocks, and two completely different truths. To an observer outside, time dilation slows you down. Your image freezes at the edge, shifts red, and dissolves into a fading ghost smeared across space-time. From your own cockpit, nothing is wrong. Your wristwatch ticks normally. Space flows, and you fall forward in steady time. Inside a supermassive black hole, you don't vanish instantly. You have hours, not seconds, of calm travel before reaching the center. Inside the horizon, space and time swap roles. The singularity is no longer a point in space ahead of you. It is a point in your future, inevitable, like next Tuesday. Even black holes die. Through Hawking radiation, quantum particles slowly leak energy away over trillions of years until the black hole evaporates. What happens to all the information crushed at the center when it finally vanishes? Nobody knows. It remains the ultimate blank spot in modern physics. Falling into a black hole isn't a single fate. It gives you two distinct endings based purely on size. In one, you are torn apart in a millisecond. In the other, you drift quietly across the horizon, already gone, while the universe moves on without you.